what's the smallest particle in the universe? At first, it sounds like a simple question. Maybe you imagine a collection of tiny spheres like marbles, each one smaller than the next. But physics doesn't work that way. The deeper we look, the more the very idea of size begins to dissolve. This isn't just a matter of shrinking down a ruler. It's a journey into the foundations of reality where our everyday intuition fails and the word small takes on a very different meanings. The first key distinction is this. Some particles are fundamental while others are composite. Fundamental particles like electrons and quarks can't be broken down any further, not with any technology we have today. They are the building blocks of matter. But protons and neutrons, the particles inside the nucleus of every atom, aren't fundamental. They're composite, made of quarks bound together by gluons. Here's the catch. According to the standard model of physics, fundamental particles don't have size at all. They are considered point-like, zero-dimensional. No width, no volume, no tiny sphere you could hold in your imagination. That means in terms of physical size, every fundamental particle is equally small, or from another perspective, the concept of size simply doesn't apply. So, how do physicists deal with this? They often turn to something else, mass. Instead of asking which particle is the smallest in volume, we ask which is the lightest. Thanks to Einstein's famous equation, E equals mc squared, mass can be measured in energy units like electron volts. On this scale, the electron comes in at about 500,000 electron volts or 0.51 mega electron volt. The lightest quark, the up quark, is already about 4 times heavier, but the real competition comes from particles that are nearly massless. Take the photon, the carrier of light, is massless. So are gluons, which carry the strong nuclear force, though they never escape the protons and neutrons they help bind. Then there are the neutrinos. These ghost-like particles are matter particles, not force carriers. And they are astonishingly light, less than a millionth the mass of the electron. Even so, they are not quite massless. Measuring their tiny mass remains one of the great open challenges in modern physics. So, who wins? If smallest means massless, the photon takes the crown. If it means lightest matter particle, the neutrino is the contender. But again, that all depends on what you mean by small. And that's the deeper issue. The small can mean different things: mass, size, cross-sectional area, or even something else. Electrons, for example, aren't little balls spinning around the nuclei. They're probability clouds, fuzzy regions where they're likely to be found. In quantum mechanics, particles are not discrete marbles, but excitation in fields described by wave functions. So, the very idea of size starts to blur. Are we talking about physical extent, about mass, about behavior? Each definition changes the answer. And maybe that's the point. The question, what's the smallest particles, says more about our human perspective than the universe itself. We grew up in a world of objects, rocks, grains of sand, drops of water, all things we can measure with a ruler. But at the quantum level, these tools break down. Here, particles are not things so much as patterns in the fabric of reality. Asking for the smallest one is like asking for the smallest note in a song. It only makes sense in context. So, what's the smallest particle in the universe? The photon? The neutrino? Maybe both, depending on the definition. But the more profound answer is that the universe doesn't obey our simple scales. The search for the smallest particle is less about finding a single thing and more about rethinking what small even means. It's a humbling reminder. Nature doesn't always fit our categories. Instead, it invites us to expand them, to keep asking, to keep looking deeper into the strange and beautiful fabric of reality. Thanks for watching. If you found this video helpful, give it a thumbs up and don't forget to subscribe to the channel.